Hi guys! So in this video, I will explain you about the correlation coefficient. So hope you enjoy the video, okay? So what is the correlation coefficient? Let me explain you. Correlation coefficient are used to measure how strong a relationship is between two variables. There are several types of correlation coefficient, but the most popular is Pearson's. Pearson's correlation, also called Pearson's R, is a correlation coefficient commonly used in linear regression. If you're starting out in statistics, you'll probably learn about Pearson's R first. In fact, when anyone refers to the correlation coefficient, they usually talking about Pearson's. And here is the correlation coefficient formula. R is correlation coefficient. Xi, values of the x variable in a sample. X bar, mean of the values of the x variable. Yi, values of the y variable in a sample. And y bar, mean of the values of the y variable. And here is the definition of correlation coefficient formula. Correlation coefficient formula are used to find how strong a relationship is between data. The formula returns a value between -1 and +1, where 1 indicates a strong positive relationship, -1 indicates a strong negative relationship. A result of 0 indicates no relationship at all. You guys can see there are positive correlation, no correlation, and negative correlation. The graph showing a correlation of -1, 0, and +1. A correlation coefficient of 1 means that for every positive increase in one variable, there is a positive increase of a fixed proportion in the other. For example, shoe size go up in almost perfect correlation with foot length. A correlation coefficient of -1 means that for every positive increase in one variable, there is a negative decrease of a fixed proportion in the other. For example, the amount of gas in a tank decreases in almost perfect correlation with speed. 0 means that for every increase, there is a positive or negative increase. The two just are not related. The absolute value of the correlation coefficient gives us the relationship strength. The larger the number, the stronger the relationship. For example, -0.75 equals 0.75, which has a stronger relationship than 0.65. Originated by Carl Pearson's about 190%, the correlation coefficient describes the strength of the relationship between two sets of interval-scaled or ratio-scaled variables. The signage R, it is often referred to as Pearson's R and as the Pearson's product moment correlation coefficient. It can assume any value from -1.0 to positive 1.0 inclusive. A correlation coefficient of negative 1.0 or positive 1.0 indicates perfect correlation. For example, a correlation coefficient for the preceding example compute to be positive 1.00 will indicate that the number of sales calls and the number of copiers sold are perfectly related in a positive linear sense. A compute value of negative 1.00 reveals that sales calls and the number of copiers sold are perfectly related in an inverse linear sense. How the scatter diagram would appear if the relationship between the two sets of data were linear and perfect. You guys can see in the picture there are perfect negative correlation and the line has negative slope and rho equals negative 1.0 and perfect positive correlation there are rho equals positive 1.0. Line has positive slope. If there is absolutely no relationship between the two sets of variables, persons R is 0. A correlation coefficient R close to 0, or we can say 0.8, shows that the linear relationship is quite weak. The same conclusion is drawn if R equals negative 0.08, coefficient of negative 0.91 and positive 0.91 have equal strength. Both indicate very strong correlation between the two variables. Thus, the strength of the correlation does not depend on the direction, either negative or positive. Scatter diagrams for R0, a weak R, we can say negative 0.23, and a strong R, we can say positive 0.87 are shown in chart 13-3. Note that if the correlation is weak, there is considerable scatter about a line drawn through the center of the data. For the scatter diagram representing a strong relationship, there is a very little scatter about the line. This indicates, in the example shown on the chart, that our study is a good predictor of exam score. Characteristics of the correlation coefficient. Correlation coefficient, a measure of the strength of the linear between two variables, like we know. First, the sample correlation coefficient is identified by the lowercase letter r. Second, it shows the direction and strength of the linear relationship between two interval negative or ratios variable. Third, it ranges from -1 up to and including positive 1. 4. A value near 0 indicates there is a little relationship between the variables. 5. A value near 1 indicates a direct or positive relationship between the variables. 6. A value near negative 1 indicates inverse or negative relationship between the variables. Testing the significance of the correlation coefficient. The correlation coefficient R tell us about the strength and direction of the linear relationship between X and Y. However, the reliability of the linear model also depends on how many observed data points are in the sample. We need to look at both the value of the correlation coefficient R and the sample size N together. We perform a hypothesis test of the significance of the correlation coefficient to decide whether the linear relationship in the sample data is strong enough to use to model the relationship in the population. The sample data are used to compute R, the correlation coefficient for the sample. If we had data from the entire population, we could find the population correlation coefficient. But because we only have sample data, we cannot calculate the population correlation coefficient. Recall that the sales manager of Copier Sales of America found the correlation between the number of sales calls and the number of copiers sold was 0.759. This indicates a strong positive association between the two variables. However, only 10 salespeople were sampled. Could it be the correlation in the population is actually 0? This would mean the correlation of 0.759 was due to change. The population in this example is all the salespeople employed by the firm. Resolving this dilemma requires a test to answer the obvious question. Could there be 0 correlation in the population from which the sample was selected? To put it another way, did the compute R come from a population of paired observation with 0 correlation? To continue our convention of allowing Greek letters to represent a population parameter, we will represent the correlation in the population. It is pronounced rho. The sample correlation coefficient R is our estimate of the unknown population correlation coefficient. First, the symbol for the population correlation coefficient is P, the Greek letter rho. Rho equals population correlation coefficient or unknown. R equals sample correlation coefficient known as calculate from sample data. Formula for T. We will continue with the illustration involving sales calls and copiers sold. We employ the same hypothesis testing steps described in chapter 10. The null hypothesis and the alternate hypothesis are H0, P equals 0, the correlation in the population is 0. H1, P not equal to 0, the correlation in the population is different from 0. From the way H1 states, we know that the test is two-tailed. The formula for T is in the below. You guys can see for the formula with N mean 2 degrees of freedom. Alright guys, that's all the explanation about correlation coefficient. Thank you for watching. See you in the next video. Bye bye.